the first thing we need to look at would be our Lewis structure. So we've done this one before. So you guys should be familiar that we have that as our Lewis structure, a positive and a negative, right? Ish. So now what we want to do is evaluate what is happening to each of those individual atoms when we look at our overall picture. Okay, so we want to know the hybridization for each of these. In determining hybridization, much like determining the electron geometries or molecular geometries and all of that, we're going back to looking at the Lewis structure and we're evaluating the groups of electrons around our atom. In 151, you would have picked the center atom. We're no longer at a center atom, so it's whatever atom I tell you to look at. Okay? So let's look at carbon. How many groups of electrons are around that carbon? We only have 2 groups. Okay? Because if we look at the top and the bottom, there's no electrons there. We only have them in the triple bond and the lone pair. So 2 groups of electrons would get us what kind of geometry? Electron geometry? Linear. I said geometry, but we'll get to your statement. Which will get us the same molecular geometry. Our hybridization would be SP. We have 2 groups of electrons. So one thing that we can kind of go through to do real quickly is say, well, how many groups do we have? Only 2 groups. So if I look really carefully at my S and P options, when I add up the exponents for my S and P, they had better equal the number of electron groups. Okay. Since by definition S, there's only one of them, that will always be 1. So what value do I need to include for the number of P's to get 2 in this case? 1. So I end up with a hybridization of S1, P1, also referred to as just SP. Okay. So if we're going to go through and look at our hybridization for our carbon, what does that mean? Well, we would hybridize our p orbital with our s orbital, and we would generate 2 new orbitals. Okay. There's one where our nucleus is our blue dot in the middle. And then our other one, whoops, theoretically the same size, our nucleus in the middle. I can't create or destroy matter, so what else is floating around? Our 2 p orbitals. Where did I center them? Okay. And this is going to get kind of ugly here. I'm going to say it's my py and my pz. I'm not going to shade that. That's a bad idea for the moment. Okay. So this would be what my carbon structure would be looking like. What would my oxygen structure look like? So we go through and do the same argument with our oxygen.
Got 2 groups again.
Put a box around our oxygen. We have exactly 2 groups of electrons, which means the oxygen's hybridization is sp, which means when we go through and look at our drawing for our oxygen, pretend we've got the same kind of system, we would end up with the same system. So our Y and our Z, with our nuclei through all of these.
You picked the Y and the Z arbitrarily, right?
The Y and the Z I picked arbitrarily. Why would I pick the Y and Z? So ultimately what I hybridized was the PX. Why would I pick the PX? I'm concerned about bringing 2 atoms near each other. What's the easiest axis to bring 2 atoms near each other on? Our x-axis. Completely arbitrary. That just happens to be the most common answer, is to bring them together on the x-axis. Which means when I look at my sp orbitals, both of those are on my x-axis. Okay. And what ends up happening is that we now want to see what happens when I bring the carbon near the oxygen. Okay. And since I'm on the x-axis, let's real quickly kind of erase some of that, clean that up a little bit. If we looked at our carbon, which I'll keep as blue, and I'll switch the oxygen to a purple color. we look at our carbon, we would really end up seeing something along these lines, right? Because it's overlaying on top of each other. Everybody okay with that? And if we looked at our oxygen, we're going to end up with something similar. Yeah. What ends up happening as I bring those atoms near each other, closer and closer? I end up overlapping, I'm just going to erase one, the orbitals here. That overlap will reach an optimal position or an optimal state at some point, okay, and then I can't continue to match them together. As I've gone through, or as I go through and do that, I will then have, I'm going to attempt to, dashing doesn't work very well, a weird looking p orbital left over there. Everybody see that that's now our p orbital? Okay, that's our py. And if we try to draw that pz, just making it look like this weird thingy. There's our pz, it's coming in and out of the plane at you. What happens with the oxygen? The exact same weird thing is going on, right? And then we've got that other one coming in and out of the plane. Kind of, sort of? Okay. If we look at this bonding arrangement, we show the formation or orbital overlap only happening in one location, which means I have one bond. But thankfully I erased that lovely drawing that I had of my Lewis structure. If we look at our Lewis structure, we should have 3 bonds. So something's missing here. Okay? There's no way I can get 3 orbitals to overlap because they're all in different axes. It's physically impossible to do that. Okay? Or at least to get that direct overlap that's happening. So that direct overlap we refer to as our sigma bond, and that's our direct overlap. So I quickly write that down. Where do those extra 2 bonds come from? Those come from our p orbitals lining up along the same axis. So as long as my py's are in the same location or the same plane, since I'm calling them y, I know they're on the y-axis, I have a new bond happening in that situation. That is now an indirect overlap on my y-axis, using what orbitals? P orbitals, so we can refer to it as a pi bond. I now have 2 bonds. I still need 3. Where's that third one? We can look at the indirect overlap happening on the z-axis. Color that different color. Another indirect overlap. That says overlap. I'm just going to pretend. On the z-axis, we have our second pi bond. We now have achieved all 3 bonds shown in our carbon monoxide structure. Okay. For those of you looking at this and saying this looks god-awful and ugly, yes, okay, it does. Particularly because if we now consider also on that y-axis, on those y-p orbitals, isn't there a bottom lobe on both of those? Can my electrons jump over there too? Yup, just as easily. So if we now start to look at all the potential overlaps, how many bonds does it look like we actually have in this? A lot more than 3 bonds.
But don't
Okay.
those 2 count as the same bonds?
The lobes of your p orbital count as one orbital. Just because we're showing a connection up top doesn't mean the connection down below is a new one. It's part of the same orbital. It's still the same connection. It is still one bond. Okay? So don't get lost in them showing lines connecting those as saying it's an extra bond. It's not an extra bond. We're just trying to show that both lobes of the p orbital can interact with each other. Okay? This is what we're trying to do with our hybridization theory, is show how these things can interact with each other to form bonds, looking at those orbital overlaps. Kind of makes sense? Okay. So, let's take a closer look at our C2H4. Okay? If we went through and drew out our Lewis structure for this, you would probably not have drawn anything that's up there right now. You probably would have gone through and drawn, come on, pen, something along these lines. What is different about what I drew in red versus the black nice drawing?
It's all on the same axis? In the same plane?
Actually, the black drawing is all in the same plane too.
It just tells you if it's sticking out or coming towards you or away from you. That's what the wedges are doing.
In the nice drawing and typed kind of system, we show the bonds as wedges and dashes, which is specifying their three-dimensional arrangement with respect to the paper. Okay? And with respect to the paper, what we're trying to say is that those hydrogens that are wedged are coming out of the board at you. The hydrogens that are dashed are going behind the board, away from you. Why show wedges and dashes? So let's take that structure, and this will be a nice visualization for everybody not at home. Maybe I'll walk over all the way over here. Let's take a look at these two hydrogens, the ones that are wedged. There we go. There are those two hydrogens coming at you, right? Okay, let's pretend I've got wings going the other direction. The hydrogen's going away. Everybody got it? Okay, what happens if I do this?
They're up. Everyone's up.
They're all up and down, right? My hands are now down, and my invisible wings are now going straight up. In the plane of the board. What's the difference between the red structure and the black structure? All we did is we took that model, or that structure, and we turned it. That's it. There is no other difference between those structures. They are one and the same. And yet we draw all these extra things on top of it. Why? Because maybe there's an advantage to looking at our structure at a different angle. That advantage happens to show up a little bit cleaner when we look at their lovely picture where they're showing all the hybridized, the pretty picture. Okay. What they're trying to show is the p-orbital overlap, which we can see in this case being nice and in the plane of the paper only because we've rotated that structure. If we take that structure and we rotate it so now all of the atoms are in the same plane, where are the p-orbitals? Coming out at you. The p-orbitals are in an orthogonal or perpendicular orbital or perpendicular plane to our bonding axis. So they've drawn it with it perpendicular to our paper so that we can see the p-orbitals better. Okay? That allows us to see the bonding overlaps both within our sigma bonds and within our pi bonds. Okay, so now the next thing we want to consider is what does this mean to our compound? And this is an interesting question. Again, with changing the view.
We can get a better idea of how it's going to interact with other things.
I don't even care about how it interacts with other things. I care right now about how it's interacting within the structure itself. So as a hint, I want you to change your view . That looks really confusing, doesn't it? What did I do to change the view? Anybody see it?
Yeah, you just turned it this way.
We took our model that if we looked at the iPad that's now coming out at the plane at you, right? Okay. Where's our double bond is on this axis. And now what I'm doing is saying, look at it here. Look at it from the end. Why does that now change our viewpoint on this? Okay, so number one, it's going to bring up a new way to look at the model. The first person to have looked at structures in this fashion, of course, gets their name associated with it, okay, which we'll talk about in more depth in Chapter 4. We do run into some issues. The front atom, let's go through on our label here. Let's call this our front atom here. And we'll call this our back atom. Okay. would you ever be able to see the back atom? Why not? Front atom is in the way. Everything that's closer to you is bigger. Everything that's further away from you is smaller, so we'd never see it. Okay? Well, if I'm trying to draw this so that we can actually discuss everything that's happening within it, we're going to do a reverse perspective on it. So that way I can see the back atom. Which means the back atom needs to be drawn bigger than the front atom. So let me add some detail here. Let's modify this. Actually, I'm just going to erase that. Why not? I'm going to draw my back atom as a nice big sphere or circle. And I want to show those hydrogens attached to it. Right? My front atom needs to be smaller. What's smaller than a circle? A dot. Good answer. And don't give me a smaller circle. I heard you. Okay, you'll notice also that when we looked at our initial drawing, we said all of the hydrogens were in the exact same plane. So that if I rotate this as I'm talking about, and I'm taking that front atom and bringing it forward, should I be able to see the hydrogens behind?
No.
No, because they'd be overlain by the hydrogens in front. How did I adjust my drawing? Just tweaked them a little bit off axis so I can see them. I now have another viewpoint for my molecule. Okay. Does this help you see something that could potentially be happening within these different types of bonds? Where's the sigma bond currently? Hidden from view. Okay. It's on that axis coming in and out of the board. Where's our pi bond? Should be up and down. So let's add that information to it. Here's our p orbital from the back one. Here's our p orbital from the front one. When do I have a pi bond? When those two directly overlap. So now what I'm going to do is take that front atom, the red one, and I'm going to rotate it to the right. I'm going to leave the back one alone. What happens when I do this rotation? Try to do this right, and I'm going to rotate it 90 degrees. So this is a 90-degree rotation. If I don't actually do it 90 degrees, please don't make fun of me. I think I got it. If we look at our initial drawing, we have overlap, right? After we do the rotation, what happened to the overlap? It is gone. What does that mean? There's no longer a bond there, which means our electrons are now just kind of freewheeling. Is that a good thing? No, they are now reactive electrons. Okay. By removing the bond, I have now increased the energy for the overall molecule. All things in all chemistry strive for lower energy states, which means what about charge? Neutral. By doing the rotation, I am now charged. What does that mean that rotation is? To do the rotation, I would have to input energy. True. That rotation does not happen. Okay? So we'll say does not happen, and then this is everybody's favorite. Right? That's an absolute. It does not happen. Easily. Okay. Under most circumstances, we do not rotate that bond. It requires a massive input of energy, something to facilitate that bond rotation. What does that mean for us? Okay. That means if I have a pi bond, I cannot rotate about that bond. What if I had a sigma bond? Why can I rotate about a sigma bond? We go back up to our initial drawing, the nice pretty one up there. There's our overlap for our sigma bond. What happens as I rotate those? It stays overlapped. It doesn't matter the rotation I do, I always have overlap, which means I will always have that sigma bond. So our sigma bonds have the ability to freely rotate. Our pi bonds cannot rotate. So,
So since the sigma bonds can rotate, does that change how those molecules interact with each other?
because the sigma bond rotates, is that going to provide us more or different energies or interactions? Absolutely. Chapter 4. Yes?
So if we had two pi bonds, could we rotate by 90 degrees?
To rotate to 90, what do you first have to rotate through?
So there's no truncative.
So if I'm 0, to get to 90, what do I have to do? Ooh, that was a bad angle to go. 0 to 90, what do I have to do?
All the way between.
I have to rotate all the way in between. Okay, so if I had two pi bonds, I do have the potential to rotate 90 and now I'm overlapping again. But what happens to do all of that rotation? It takes energy. I no longer have that overlap. Now I have the overlap again. That rotation is again prevented. You will, if you draw your structures for things that have triple bonds, notice it doesn't matter. That we end up not worrying about it in triple bonds. Okay? What this is going to end up telling us is without that rotation in a pi bond, when we look at different structures, say in this case, I'm now inserting an R group, which in my terms usually means anything, but it very typically means carbon. It means typically not hydrogen. If I now compare these two structures, are they the same? No. The only way they could be the same is if I could rotate. Did I draw them right? Yeah. Is if I could rotate about that pi bond. If I do that rotation, I can get that bottom R group up to the top. But because it's a pi bond, I cannot rotate, which then means these structures are different from each other. Make sense? And as soon as we have something that's different, we call it bad names, right? Did it when we were kids, we're doing it again. We now have two things that are different. We must name and identify that difference between them. Because the number of atoms are the same, the bonding is the same, the only difference is the arrangement of those atoms with respect to our bonds. So we have to come up with a way to name that so that everybody knows what's going on within it. That name we use is referred to as cis and trans, or more correctly, as we'll discover when we get into nomenclature, E and Z. I did that one wrong. Z and E. Okay. So, what do they mean? Cis means that they're on the same side. What are on the same side? Cis and trans is an arbitrary system to identify the relationship of any two groups. Okay? This is why it's not a nomenclature system. Because naming needs to be very specific and apply to everything. Cis and trans only applies to two groups relative to each other. Okay? And you're right, it's in reference to on the same side. If we're now going to look at our structure, say that first one, what two groups are we going to reference to help us identify the difference between cis and trans? Where does hydrogen show up in your structures? Someone said it over here, I think. Everywhere. Hydrogen is everywhere. Is it going to be a good idea to develop a nomenclature system based on an atom that shows up everywhere? No. We want to pick something that is much more selective than looking at hydrogen. So we're going to pick anything other than hydrogen. In this case, it'll be the R groups. Where are the R groups? Same side. So a lot of you are saying same side, which is our cis. This is an interesting question. You are saying they are on the same side. Are they really on the same side of that line? No. Not the line I just drew. It's all with respect to the axis of the double bond. Our double bond is running through here. They're now on the same side of that double bond. The official nomenclature system that you would need to do to reference this, and again, you don't have nomenclature rules yet, so don't stress on that, would not be referring to it as cis, but referring to it as a hint, I lined it up, Z. Another way to help you kind of remember this, cis is on the same side. Okay? Which then, process of elimination, what's happening in the next one? We're looking at opposite sides with respect to our bonding axis, which then makes them trans, and we would then refer to it as E. Okay? How do you remember which one's which? I don't know, I don't care. Come up with something. Okay? The same side is the only one that's worked for me. Okay? And even as I say that, you notice that when I first drew it up, I did it wrong. Okay? And I actually had to say it, I didn't do a very good job mouthing it out, but sometimes you'll see me mouth that out. Z, same, Z, cis. Okay? I don't care how you get them nailed down, but you do need to know those distinctions. Okay? So let's take a look at these molecules. Do these molecules exhibit cis-trans isomerism? Meaning, if I rotated that double bond, would I end up at a different structure? Okay? Then I know I have a cis-trans system. Okay? So, take a look. Let's pick the last one. Does that molecule have cis-trans isomerism? I like how nobody's drawing out the structure. And by like, that's sarcasm. To determine cis and trans, we need to see the groups with respect to the double bond. How many groups are shown on the double bond right now? One at best. Every double bond will have 4 groups. If we only see one, we'd better draw on the other 4. Okay. Would this molecule exhibit cis-trans isomerism? If I rotate about that double bond, would I end up with a different structure? Why not? These hydrogens are identical. When I swap, or I rotate, I put a hydrogen in the exact same location I had a hydrogen. I can't tell the difference between the structure. The other option you guys ran through and did, it said cis and trans, we needed at least 2 groups. Okay, we don't have 2 distinguishable groups here. Okay? Oof. Please connect. Okay? So, no. Next one.
Are we considering the molecule pin?
You can consider it whatever you want. Does it have cis-trans isomerism?
They're all carbons.
Oh, we're getting a lot of mix-up here. So let's take a minute, talk to the people around you, see what you can come up with. We'll run around. I'll point to each table, and each table is going to tell me yes or no.
All 4 of them are carbons. So if you switch it, it doesn't matter.
The answer to the first question, does that structure exhibit cis-trans isomerism, is no. There is no cis-trans isomerism there. By adding the chlorine, does that change the answer? Yes. Okay. I have no idea what you guys guessed. I don't really care.
So the
Just
reason,
wanted you to commit.
the reason why I picked no for the first one is because if you rotate around the pi bond, you just end up with a mirror of the first one.
You have to be careful with mirrors.
So
Okay, because if you say mirror, my left and right hand are mirrors and they are not the same.
Right. You end up with a 180 rotation of the same structure.
So remember, in deciding our cis-trans is, do we end up with a new unique structure if we rotate about that pi bond? If I rotate about that pi bond, do I end up with a new unique structure? What is the difference between CH3 and CH3? Nothing. Just like the case we had with the hydrogens. So if I can't tell a difference between the groups on one half of my double bond, I won't have cis-trans isomerism. Okay. And one of the suggestions that got floated out there, not name any names, was they all carbons. All having carbons isn't necessarily the issue. It's, are those carbons different? Can you tell a difference between them? Hence the statement of changing the question and now adding a chlorine there. Does that change the answer? Well, can I tell a difference between this carbon and this carbon? Now I can, because I have a chlorine on one and hydrogens on all the other.
Even if that was a carbon.
Even if it was a carbon, it could be any atom out there other than hydrogen. Okay?
Question.
Yes?
With the other extra carbon on like the bottom half of that, does that make any difference or not, because the top two were both the CH?
When we are trying to determine cis-trans isomerism, it would be nice if we had kind of a rule set to apply. Okay, that rule set pops up when we look at nomenclature, but let's walk through our rule set. Number one, take your double bond, cut it in half perpendicular to the bonding axis. Okay. Now what I want you to do is look at each half. Can you tell a difference between those? No. Right away? Does not have cis-trans isomerism because you can't tell a difference between those atoms. What it will eventually become is, if you can tell a difference, which one is more important. So let's look at the other half. We're looking at carbon versus hydrogen. Can we tell a difference between those two atoms? Yes. Ultimately, to decide, at this point, all I'm saying is it cis, do we have this isomerism? I'm not asking you to define, is it cis or trans? So our answer is yes. But if we now had to define cis or trans, we need to decide which of those atoms is higher priority, the hydrogen or the carbon. You said carbon, and your answer would be correct. Good job. Why is carbon a higher priority than hydrogen? And honestly, I'm not 100% on the rules for this. I need to look it up so I can memorize it eventually. But there's only a few exceptions to it. It comes down to either atomic number or atomic mass. Anybody know which one it is? Okay. So it's one of those two, and literally there's two exceptions on the periodic table, depending on which way you look at it. So it's not that big a deal. You remember one of those two, you're fine. Carbon has a bigger atomic number than hydrogen. It also has a bigger mass. Okay. So carbon is our higher priority, so we would star that carbon. Then to evaluate which is it, cis or trans, then we would look on our parallel axis and say, where are our starred atoms? Okay, so we just picked two examples that were neither cis nor trans. Okay, we okay with that rule set to not walk through it for that next one? Okay, so let's look at the next structure. Let's do the full rule set all the way through. So we said, first step, cut perpendicular. Okay, and we'll look at each half. Let's look at the right half first. Hydrogen versus chlorine. Are they distinguishable?
Yes.
Yes. Okay. Look at the left half. Are they distinguishable?
Yes.
Yes. Do we have cis-trans isomerism? Yes. Now the fun question, which is it? Cis or trans? Okay. To establish that rule, we now have to go through and assign our priorities. We're comparing hydrogen to chlorine. Which has the higher atomic number? Chlorine. Move to the left half. What are we comparing? Carbon and carbon. Ouch. Can we tell a difference in atomic number between carbon and carbon? No. So we know there's a difference here, but how do we apply the rules? Okay. Sort of. Our rule comes down to comparing atoms only. Is there a difference between carbon and carbon? No. So what we will do is move out to the next atom. And we'll move out to the next highest priority atom, which is carbon on the bottom molecule. We'll color it differently. Carbon on the bottom molecule, and we move out to the next one. Carbon on the top. Well, can I tell the difference there? No. Okay. Are there still other atoms connected to that first blue one that I'm trying to do my comparison on? Yeah. So let's go back to that blue atom and see what the other atoms are. I go out to my next highest priority atom being hydrogen versus the other one, carbon. Is there a priority difference between hydrogen and carbon?
Yes.
Which is higher priority? Carbon, which then means which is starred? The carbon on top gets starred. Okay. It is solely atomic in deciding priorities. Are there other goofy rules that fall into this? Yeah, we'll deal with it, but not right now. Okay. Now that we've got our stars, we have to decide, are we cis or trans in this conformation? Our last step, cut parallel to the double bond. And we need to find our stars. Are our stars on the same side or opposite sides of that line? Same side. This is the cis conformation. Okay? Do the last one, all by yourself. Talk to the people around you. See, what do we think? Does it have cis-trans isomerism? No, it does not, which is all sorts of weird, because if we run through all the rules that we just went through and did, you would end up starring here and here. We cut, whoops, parallel to the double bond. Those stars are on the same side. We would suggest cis. And you are correct. That is a cis structure, but that does not exhibit cis-trans isomerism. The cis-trans isomerism means I can have both. I can have the cis form and I can have the trans form. Can I make the trans form? It is going to be physically impossible to keep that as a ring and somehow rotate it to get the trans formation. We don't have enough distance to loop around the double bond. As soon as you move into a ring, the trans form disappears for a little bit of time. Okay, what is that little bit of time?
Is that when you have two rings?
Nope.
Okay, just checking.
We said the transform does not work because it is physically impossible for me to connect the star, have it drawn on the other side, and still connect to the other star. Why?
You can't like split it.
How long are those bonds?
Oh, it's equal.
They're sigma bonds. They're all equal to each other. They're relatively short. The distance to bridge that gap is longer than those three bonds. So it cannot reach the trans form with this structure. When could it potentially reach the trans form?
Would that be if you had like p-orbitals? Or
Nope.
just even like a triple bond?
A bigger ring.
A bigger ring, okay.
Add more atoms in between your trans form. Now you can bridge that gap all the way across and still have a trans double bond in a ring. I think it's 8. I think you have to have 8 carbons in your ring minimally to achieve a double bond, a trans double bond in a ring. After that, it becomes progressively easier and easier. Anything under 8, it can't do it. It cannot physically bridge that gap.
So if you had 8 atoms all around and you flipped it, would it make like a figure 8 type structure, or would you actually have to like break those?
Depending on your viewpoint, it would look like a figure 8, yes. It still has to be open all the way through. Okay? So it's just kind of one of those weird things you got to watch out for. So your rings don't give you cis-trans isomerism because you can't make the trans. Okay? Okay, now something a little bit near and dear to my heart that I particularly like that nobody else seems to like. I'm also not the greatest at it, but I think it's fun. So we're going to take a look at it. When we move up to the molecular picture, we need a better way to represent our bonding systems. Okay, and this is where we run into the Lakow model, the linear combination of atomic orbitals, which, if you remember, said requires a bunch of computers. So what we've come up with is kind of a pseudo-Lakow model that allows us to still come to some of those same predictions and uses that the full computer model will do. Okay? And this is going to come back to the quantum mechanics of how an electron moves. When we look at electron motion and existence, it moves in the form of a sine wave or a cosine wave. Okay? So it has ripples associated with it. Okay? And we can have a positive trough and we could have a negative trough. If we're going to go through and make a bond, we're now taking one orbital, which is a sine wave, and another orbital, which is a sine wave, and we're bringing them near each other and seeing what happens. Okay? So let's say this is my origin. This is my origin here. What happens if when it encounters the other wave function, it looks like that? Okay. We have peaks matching peaks. We have valleys matching valleys. The signal that we get out of it amplifies. What happens if instead we saw the bottom system? It flatlines. The existence of our electron has to be on this wave pattern. If there's no wave pattern, can the electron exist there? No. We refer to that point as a node. Okay? So depending on how our orbitals interact with each other or overlap, we can get them overlapping in a way that is constructive, and we amplify the existence of the electron at that point, or they overlap in such a way where they counteract each other, and we de-amplify, cancel,
Would they even interact anymore?
cancel each other out, and we no longer get the electrons existing there. Okay? That's what we're looking at within these systems. Every time we look at an orbital, we have to realize that there are phases associated with it. And when we draw an s orbital, it's just a sphere. So how many phases are there? 2. That's really weird. A sphere only has one shape, though. How can it possibly have 2 phases? There's 2 possible states that the sphere can exist in. It is either all positive or it is all negative. So that when I go through to add these orbitals to each other, I then have to look at them. How are they aligning? Are they aligning positive to positive, in which case it's the same phase, and we get an additive or amplified system where my electrons can now exist, or they're in opposite phases, and it flatlines, and I don't get electrons existing where they overlap. Okay? So what does that mean? Let's ignore the possibility and result. If we looked at, say, the bonding for hydrogen. Okay, a hydrogen molecule looks like what? It does not look like a proton. A hydrogen molecule looks like what? A molecule, good. There's an extra word. Diatomic. Does not look like a proton. A proton does not have a bond. It is H+. We now have a bond between 2 hydrogen molecules, or 2 hydrogen atoms. What we are trying to describe is what is happening in that bond that makes this a molecule. Well, that needs to be an orbital. That orbital cannot be an atomic orbital. Why can it not be an atomic orbital? Because it's a molecule. Atomic orbitals belong on atoms. We're no longer at an atom. But how did I get to the molecular orbital? It had to combine from my atomic orbitals. So what I'm going to look at, or what are the atomic orbitals for the hydrogen on the left? What are the atomic orbitals for the hydrogen on the right? And I want to see how they interact. And in particular, their valence. What is the valence orbital for hydrogen? An s orbital, which looks like a sphere. And the other one looks like a sphere. What happens if those orbitals are in the same phase? amplifies the signal. So what we're describing is that we now bring those atoms near each other where they are aligned in the same phase. We're asking about that area in between. Let me draw it up here. I'm not very good at drawing today. We're asking what is happening in that shaded area. Okay. If they're in the same phase, what happens to the signal? It amplifies, which means where can the electrons exist? In that area. Where should that be relative to my atomic orbitals? Higher or lower in energy? I'm amplifying the existence of electrons. The energy is going to be lower. So if I'm going to look at this possible interaction where they are in the same phase, I'm going to be at a lower energy state for my molecular bond. Well, does that make sense? Should a molecular bond be lower in energy than the atomic bond? Absolutely. If it was higher in energy, we would never form molecules. We would stay as atoms. We don't want to be high energy, we want to be low energy. Okay, so it makes sense that we're drifting lower. By showing that overlap, we are saying that we have increased the likelihood for electrons existing there. What does the sphere represent? The likelihood of electrons existing in that space. If we go through and show how those two overlap, we just said the electrons are more likely to exist in that space. So what would my new molecular picture look like? If these are my nuclei, where would I expect to find the electrons? I should see an increased likelihood between the atoms. And I now have the picture of my molecular orbital. What happens if they're not in phase? It flatlines in that overlap between the atoms. Should that be higher in energy or lower in energy than my atomic orbitals? Should be higher in energy. We're saying electrons, you cannot exist here. Right? If we told you you can't exist in an individual location, that's when you get irritated and start to fight somebody. Okay? Birth of all wars, isn't it? So we're at a higher energy state. How would we draw our electrons then? Where would we expect our electrons to exist? Those were our nuclei. Away from the middle. What if we generated right in between? A node. By adding a node, we have increased in energy. Look at all those pieces sort of falling together. Sort of. Okay. We now have a molecular orbital diagram for hydrogen. Okay. One thing that's missing from this is we haven't specified the electrons. Well, how many electrons am I looking at in this system? How do I know it's only two? Well, there's hydrogen. The formula was H2. It has only 2 electrons. So where are those 2 electrons? Well, in the atomic picture, each hydrogen brought in 1 electron. I now move to my molecular picture. I need to put those 2 electrons into my molecular picture. Where do I put them? Okay. So I heard an answer of some in between. Do we have electrons between the first energy level and the second energy level? No. Why not? Electron orbitals are quantized. They are in definite orbitals. We don't have anywhere in between. We have to exist in an orbital. We have 2 orbitals. Where do I put these 2 electrons? So I heard at least one person say the answer, so let's run it again. Hydrogen, you said it had what orbital? Be more specific. 1s. Why'd you not say 2s? 2p. 3s. What's that? Okay, why? Where do you put your first electron? The lowest energy. Not in the 1s, the lowest energy. That's where it goes. I have 2 electrons. They need to go into the lowest energy molecular orbital. Where's the lowest energy molecular orbital? The one at the bottom of my list. There goes my first electron. Da-dum. Where's the next one go? Why next to it, not go up to the next one? Every orbital can hold 2 electrons because we have opposite spins on electrons. There's the second orbital. What happened to the overall energy when I made this bond? It went down. Is it likely to find hydrogen as a diatomic molecule? Yes. Why? The energy went down. Here's a fun prediction. That's not the eraser I wanted. H2 minus 2. Should that molecule exist? We have a molecular orbital diagram that describes the molecular orbitals when we bring hydrogen near another hydrogen. What is different about H2 minus 2 that needs to adjust our figure? It has 2 more electrons. I'm not starting with just a hydrogen atom. I'm starting with a hydride, which means 2 electrons on both sides. Where do those next 2 electrons go? They go into the upper one.
Would that be considered a p-orbital?
That has nothing to do with a p-orbital, and we'll talk about what that means in a second too. What happens to the overall energy now of this diagram? What do you mean it's greater? How did it increase? I've got one low and I've got one high. Why did it increase?
Wouldn't it have decreased because the 2 atoms are increased in energy to begin with?
Our atoms are here. Our bonding orbital was lower in energy. Our constructive overlap was lower in energy. Our deconstructive overlap was higher in energy.
Yeah, but I'm referring to that hydride. Because
Okay.
wouldn't the hydride make it go up in energy?
Nope.
Okay.
To a first approximation, no. What do we think? How far down in energy did this go? Give me a number. 2. How far up in energy did that one go? Okay, let's run with 2. Is this higher or lower in energy than the starting atoms? I have electrons with a lower energy of 2. I have electrons with a higher energy of 2.
They're going to negate each other.
They are even, which would mean
It's going to be flat.
the exact same energy. So there is no real favoring one way or another. How many of you have seen H2 minus 2? Okay, let's try it the other way. How many of you have not seen H2 minus 2 before? That's a little bit better. Okay. So if we just said it's an even flat line comparison between these, why have we not seen it before? Because according to our energy diagram and what we've been putting together, it says that it is equally likely. We made a bad assumption. The deconstructive interference is a higher energy gap than the constructive interference. Which means if I put electrons into that deconstructive interference, it starts to destabilize the molecule. If it's an equal relationship, our overall molecule is now destabilized, higher in energy than my starting atoms, which means shouldn't form because it's higher in energy than my starting atoms. Okay. How much higher is it? We don't quantify it because it's not physical organic chemistry. All we know is that it's higher than. We want to come up with some names so that we can reference these. Constructive and deconstructive works well, but those are big fancy terms. Let's come up with another way to describe these. Okay. What happens when I have electrons likely existing between 2 atoms? I have a bond. So a good way to describe that bottom situation would be to call it bonding. In the upper case, do I have electrons between the atoms? No. So a bad thing to call it? Bonding. It would be a horrible thing to call it. So what should I call it? Okay, we can run up with all sorts of possible options. If we say non-bonding, we run into a slight gray area because we've seen non-bonding electrons show up elsewhere. These aren't those. Because we're saying in non-bonding we have electrons existing on an atom. Here we're saying the electrons cannot exist. Eee. So using the word non-bonding, we've got a weird gray area. But it is also not a bond. As some people have alluded to already, there's another term we could use. Anti-bonding. What happens when you bring antimatter near matter? Annihilation. What happens when you fill an antibond and a bond? Annihilation. It doesn't exist. Okay? We now have the basics of molecular orbital theory. We take two orbitals, we look at how they overlap. Do they overlap constructively? Lower in energy. Do they overlap deconstructively? Higher in energy. Every time I overlap my orbitals, how many molecular orbitals did I generate? 2. I start with 2 atomic orbitals. I need 2 molecular orbitals. I start with 20 atomic orbitals. I need 20 molecular orbitals. Of those 20, how many are antibonding? 10. Why? Every time I overlap orbitals, I get a bonding and an antibonding. Every time. Okay? Questions? Good, let's make it more difficult. We don't always overlap s orbitals, we also can overlap p orbitals. So let's form a bond on our x-axis. What happens on that x-axis as I bring these orbitals closer to each other?
Yeah, an overlap
Where?
in the x-axis
Between what?
between the two, between px and
The two px orbitals will now interact with each other. So there's one px, there's the other px. Okay. If that is a constructive overlap, I've now increased the likelihood of finding the electrons in between the atoms. So a better way to draw this notice that even as I did this, I've now formed a bonding interaction, but in that bonding interaction I have 2 nodes. The electrons cannot exist in that space. Why do I still need those 2 nodes? How many nodes are in a px orbital? 1. How many px orbitals do I have? So how many nodes do I start with? 2. How many nodes do I need to end with? 2. What happens if they deconstructively overlapped? How many nodes do I have? It can't be 2, because if it's 2, I'm at the exact same energy as my bonding. Okay? I now can't have electrons existing between the atoms. Okay? So I have another node. Okay? What happened to the pz and the py? I heard the same thing, and I would argue that's not true. What's going to constrict and prevent the pz and the py from overlapping like they do with the px? We are bringing these atoms close to each other on what axis?
the x-axis.
The x-axis. The px will overlap first. What happens to the py and the pz? They are indirect overlap. They never directly overlap with each other, and what we'll end up seeing would be an indirect overlap between this. But how can we show that we get an indirect constructive and an indirect deconstructive? This comes back to how we look at our p orbitals. Our s orbital, we said, could exist in 2 possible states, a positive and a negative. And since there were no nodes, we could only look at it as one thing. Our p orbital has a node. What is the difference between the top node and the bottom or sorry, the top lobe and the bottom lobe? Nope. It rhymes not with that word. I can't come up with a rhyme with it. Phases. The top lobe is out of phase with the bottom lobe, which means if I now look at a normal interaction, and I don't have enough space to draw all these, so I'm going to have to erase the other interaction that we drew up there. We now want to say that that top lobe is in the same phase on both of these orbitals. So how could we define that or draw that?
Same shading.
Easiest way to do it is shading. We're now saying that these are in phase with each other, which means the electrons can exist and jump back and forth across. And we end up seeing this kind of system as our molecular orbital. What happens if they were out of phase with each other? And now we have more nodes. Where are nodes in the first one?
Across the x-axis.
Across the x-axis. Our electrons can't exist there. If we look at the out of phase one, we still get across the x-axis, and we now get through the y-axis between them. Two nodes. You increase the nodes, you increase the energy. Okay? This can be used to explain our pi bonding. To generate that indirect overlap, it's p orbitals sharing across in the same phase. What happens if we rotate? Those p orbitals no longer overlap with each other, and what happens?
They repel each other?
We have a new node. A new node means more energy. We can't do the rotation. There was a question, I think.
That was my question. So this is what you would see if you rotated that, and you would end up with,
You
because you have to add energy.
disconnect it. Yep. Exactly right. Okay. We will kind of periodically keep coming back to molecular orbital theory. It plays a much larger role in second semester. Some students get it and can manipulate it. Other students just kind of memorize it and deal with it. All we're looking at is, do they overlap? Constructive, lower energy. Do they not overlap? Deconstructive, higher in energy. We end up generating a bond in the lower case where it's constructive. In this case, we could refer to it as just a bond and an antibond. But was it different than our initial system? Well, our initial system, we had a sigma bond. Are these sigma? No, so we could call these pi bond and pi antibond. How many of you wrote all that stuff down? Yeah, I noticed lots of you writing. Okay. Difficult to write out. Pi star, meaning antibond. Bond, just pi.
So could you do the same notation for sigma?
And you can do the exact same thing for sigma. Your bonding sigma is just a sigma symbol. Your anti-bonding situation for a sigma bond is a sigma star. Okay? So if we looked at a molecular orbital diagram, this is telling you there's 12 atomic orbitals. How do we know there's 12 atomic orbitals? Any guesses as to the formula for this compound? C2H4. How do we know there's 12 atomic orbitals? Hydrogen has what atomic orbitals? The 1s. How many hydrogens are there? There's 4 of them, so we end up with 4 atomic orbitals coming from hydrogen. Carbon has which atomic orbitals?
1s.
Ooh, interesting. You brought in the 1s. Officially, for molecular orbital diagrams in the full-on Lakow model, yes, we look at the 1s. Unofficially, do we care about the 1s? Why not? It's already filled. More than likely, it's not going to interact with another atom because it's too close to the nucleus. The 2s, or the second energy, are further away. So when we look at carbon, we'll end up with 2s, and then we'll have our 2p. How many p orbitals are there? There's 3 total. So every carbon brings in a total of 4 atomic orbitals. How many atomic or carbons are there? 2, which gives us 8. 8 plus 4, ta-da! 12 atomic orbitals. How would we guess our molecular diagram is going to look? Okay, there's a first good step. Okay, we will have our anti-bonding, and we'll have our bonding. Within that, we should expect 6 bonding and 6 anti-bonding. What else? Are all the bonds the same? I should have pi and sigma. How many sigma should I have? How'd you get 5?
Counted direct overlaps.
Look at the direct overlaps. The other option, count every single line that's by itself. You're counting these single bonds. There would be 5 single bonds, which gets us 5 sigma bonding orbitals. If we have 5 sigma bonding orbitals, we have 5 of our anti-sigma, or 5 sigma star. Is that all of the bonding in this molecule? No. What else is going on? We have the pi bond. Where should I put that pi bond? Higher or lower in energy than the sigma?
Higher.
Why?
It's a higher energy state.
Pi bonds are higher in energy than our sigma bonds. So I would expect a pi bond. How many pi orbitals should I be, or pi bonding interaction should I be drawing here? 1. Why? There's only 1 pi bond. Okay. How many pi anti-bonds? 1.
Now, can you draw it like that, or do you have to put it above the pi anti-bond?
So the pi anti-bond will be roughly symmetrical to the pi bond. So your pi bond is a little bit higher than your sigma. So your pi anti-bond will be a little bit lower than your sigma star. Okay? And we now have the molecular orbital picture. Okay? Wow, look at that.
Is the pi antibond lower than the sigma antibond because they're not, there's no direct, I guess you're pushing 2 atoms together, there's more of a
Repulsion.
repulsion.
Interesting idea to it.
Pi bonds are a little further apart.
I will admit I have no idea.
Okay.
I'll see what I can do on that. I've got a physical chemistry book. I'll look through that and see if they can explain it. Okay. What happens if we turn this into acetylene? You all done your nomenclature, right? You could have just said no. That's all I was looking for. There's our acetylene. What would we expect to change? We would have less sigmas. Why? I got rid of 2 hydrogens, 2 sigma bonds. So how many sigma bonds would we expect to see?
3.
We would expect to see 3 sigma bonds. Right, which means 3 anti-sigma bonds. What else would we expect to change? We now have 2 pi bonds and 2 pi star. Does it become more complicated if we bring in non-bonding pairs? Yes, I'll leave you to deal with that in the textbook. Okay? As kind of a hint there, are non-bonding pairs part of bonds? Should they affect the bonding in a molecular orbital picture? No. So where would you predict your non-bonding pairs to show up in your molecular orbital diagram? Where is the only neutral state in our molecular orbital diagram? Right through our middle. That's where our non-bonding energies will show up. Okay? Some interesting results come out of this, particularly back to hybridization. If we look at each of our structures here, C2H6, I'm not going to draw the hydrogens, but I will show the bonds. C2H4 and C2H2. What is the hybridization of the carbons in the first example? sp3. Second example, somebody else. sp2. Oh, and I was about to say somebody else again, so beat me to it. Those are our hybridizations. What changed?
Number of pi bonds.
So we could reference the number of pi bonds, yep. What happened to the percent S character for the carbon involved? It went up. If we look at our sp, it is roughly 50% S. And the other one, it is 33. Did I do that right? And 25%. Should that matter? Ooh, okay, well, if you're going to say yes, then I don't have to explain why. What do you mean energy? Higher energy in what molecule? sp3 is going to be higher in energy. Okay. What's happening with the carbon hydrogen bond in the CH or C2H2? It is more S character. So what is the difference between an S orbital and a p orbital? Different energy, yeah. How would we represent that different energy? Could look at nodes, keep going.
How far away it is from this?
Distance from the nucleus. The more p orbital characteristic associated with it, where are the electrons?
Further away.
Further from the nucleus. The more s, closer to the nucleus. And since we're looking at bonding, when we move to sp character atoms, an sp hybridized carbon atom is doing what to its bonding electrons? Are they closer or further from the nucleus? They are closer. So the sp carbon is holding its electrons tighter than the sp3 carbon. Well, that doesn't really matter. We never looked at the ability for an atom to hold bonding electrons before. That's completely irrelevant to all chemistry, right? No was a good answer to that. Because reactivity, and we would classify that difference using electronegativity. The less hybridized our atom, sp, the more electronegative it becomes. Does that matter?
Yes.
Which of those hydrogens is easiest to remove from the structure? The sp. The carbon is more electronegative than the hydrogen. It is pulling those electrons away. Does that change the reactivity? Heck yes. The sp carbon becomes acidic. The sp3 has virtually no acidity. It's a hybridization effect. Okay? We have to stop there. All it is just kind of a review slide. That's the last thing on molecular orbital theory. And then we're moving into, I believe it's chapter 4. Almost chapter 4. Yeah, it'll be chapter 4 then.